today I will introduce you to the convolutional neural network. So it will be a short introduction. What I would like to do is to give you some intuition, but it's not to going into too much details. So I would like you to know if you can apply it to your own field of research. So going directly to the historical introduction. So first of all, what are deep architectures? These are architectures that are combining different levels of non-linearities and so convolutional neural networks are part of deep architectures. First of all, the first milestone in that research is neocognitron paper from Fukushima. Fukushima used the research of Sobel about the cat's vision system. So the vision system is made of two kind of cells: the simple cells, S cells, that we could refer to convolutional cells in our networks, and the complex cells, pooling cells. So you will understand that a bit later, but it's to emphasize the fact that that kind of network has its source in the human body and in the brain. The second paper is published in 1998 and is written by LeCun, Bottou, Bengio, and Hafner. It's a very well-known paper that introduced a very well-known network, Lelets 5. I will give more details about it a bit later. You have to know that before 2006, deep architectures were not really used because it took a lot of time and it was difficult to run. But after 2006, some new papers appeared in order to run that kind of model, like GPU computing, with the paper presented there, and in 2009, with a new paper from Bengio, introducing a new technique for deep architecture. Going back to the paper I told about, so gradient-based learning applied to document recognition. The paper based its research on the MNIST database, so database for digit recognition. It's a very well-known database in that kind of research. They exposed the fact that the classical approach is to divide the research in two phases. The first one is the feature extraction. So you try to extract feature based on your own knowledge of the field. So you need knowledge about the specific field, like in biology, and then you apply a general classification algorithm. For example, if you want to detect handwriting, like sentences, you have first to apply a field locator, then field segmenters to segment the words, and finally the letters to recognize that it is a letter when you segment it, and then apply like some post-processor. So you divide it in 4 steps, and that is the classical approach. It is mostly based on low feature space, and the emphasis is placed on feature extraction. Now, what are the factors of change? Because we went for a classical approach to a more complex one with convolutional neural networks, and the paper explains that there are 3 main factors of change. The first one is the power of the machines. The second one, the large database that help to run new models. And the last one are the algorithm, like I told you about GPU computing, no, sorry, it was for computing, but for algorithms like backwards propagation and other algorithms that can be applied in that context. So that is the model that they finally presented in their papers. So they tried different models, but they came up with that model as final step. It's Lelets 5, very well known. You can see that you have many kind of layers. You have here convolutional layers and then pooling layers. Convolutional, so C stands for convolutional and S for pooling. And finally, you have fully connected layers. So for you, it might be a bit a bit complex, but it's it's well thought, and I will go into more explanation about convolutional layers and pooling layers in coming slides. But you can see that it's close to basic neural networks, but there are some layers that differ. They took as input layer images from 2022 pixels, and they added zeros around the image to create a 32 image. It's why do they that? It's to keep the image to finally end with a 2022 image, because when you go through the model with the convolutional layer, you reduce the image because you reduce the dimensions, and so to keep the information, they try to start with a larger image and to finally end with less pixels. Some more information about the network, but that's not so important. So now the basic principles of that kind of network. Why do we use convolutional network rather than fully connected network? The first advantage is that with convent we can take advantage of spatial structure, and it's really the main advantages of it. The second point is that you don't need a lot of pre-processing. You don't need specific scientific knowledge in the topic. If you are dealing with biological data, you don't need to be an expert in the field. And finally, you have less memory requirements. So what is a mathematical convolution? As you can see, it's just a recall for you because it will be the core function in our network. So it's like you have one dimension, then one function that doesn't move, and then you move the other, and you make the product, and you sum all the product. But I think you know about it, but it's just a presentation there. You have three basic concepts in that kind of model: local receptive fields, shared weights, and pooling. So what are local receptive fields? Here you can find a definition out of Wikipedia, but the definition is based on human body, but you can see that the definition can also be applied in our network. So it's really based on how the brain works. So you have neurons or units in your network that are only sensitive to a small space in the previous layer, and so you won't connect the neuron to all the previous layer neurons, but you will just choose a small space, and it will be the receptive field of that neuron in the next layer. So if you do that, all the receptive fields are overlapping, in fact, because you take. I will have a picture so you can see better, but it will overlap. And you have some details, the stride length, for example. You can move one neuron by one neuron, or you can move by larger steps. So these are details in your model. You have hyper parameters that you can train, not train, but that you can decide. So here a picture. We are in a two-dimensional example, so like 4 images, but you could be in 3-dimensional or 1. But I think it's the best one to really understand what is a convolution. So for example, here you have your input neurons, and here you have the first hidden layer, and you can see that what will be the value of that neuron here. It's just a value, a figure. It will be the convolution of the weights of the weights of that layer. So weights will be trained with that surface of the space. And for the neuron next to it, it will be the same kind of surface, but just shifts by 1 unit. And so you apply the same shift, 1 unit, and then over the whole surface. So why did I talk about shared weights? It's because for each layer, you have a specific feature map. I mean, for each layer, for each convolutional layer, you can have different feature maps, but each feature map is determined by a kernel or a filter, and a kernel or a filter is determined by its weights and its bias. So it's like in normal networks, normal neural networks, but here we don't have weights and bias for each neuron in the network, in the layer, but all the layer will have the same weight and bias. So they share the same weights and bias. On this picture, you can see that, for example, each line with the same color has the same weight. So you apply the same weight on each neuron, and here you can see that the receptive field of the neuron is 3. Is 3 because you have the layer M that is taking as input three inputs. I mean 3 neurons from the previous layer. So here the receptive field is 3, but it's just a picture. So you must adapt it each time. So with shared traits, you have less parameters in your model, so you reduce overfitting, and it's one of the best advantages of that kind of network. Last point is that a feature map is trying to determine a specific pattern. So if you, for one convolutional layer, you can have different feature maps in parallel, and so each feature map will try to extract one pattern from the previous layer. So it's for pooling. So you have in your model convolutional layer with the function of convolution, and you can have pooling layers as well. It's in general used after the convolutional layer. You have a pooling layer that can be temporal spatial subsampling. Here the goal is not to really create new information, but it's to simplify the information, because in a convolutional neural network, we try to make the network invariant to shift in the space. And so if you pool the information, if you simplify the information, you try to make it spatially invariant. So here it is whether a given pattern is found anywhere in a region of the image. So anywhere in a region, that means you determine the length or the dimensions of your pooling, like say 2 by 2, and then as you can see here, 2 by 2, you will summarize that information for that region into one neuron. And what kind of function can you apply here? You can apply, for example, the max pooling function. So it's just the maximum of the 4 neurons on the picture. Here we don't have overlapping of the region, and it can be applied to each feature map. Just a small point on the dimensions. If you start with a k by k region, and if you start with a n by n input layer, and you have a k by k region for your pooling, finally you end up with n divided by k squared new layer. That's basic. It's not that complicated. Coming back to the Lelets 5 model network, I wanted to give a small intuition on how to link convolutional and pooling layers, because I say that you can have, for each convolutional layer, you can have different feature map. That means that, as I showed you on the big network, you can have parallel feature maps for one layer. So one layer is no longer characterized by only one feature map, and it is maybe what is a bit strange for that kind of network. And so how could you link the pooling to the convolutional layer? You could link every neuron in the next convolutional layer to every feature map determined by the pooling layer previously applied. Or you could decide, no, I don't want to link every neuron to every feature map, I would like to make like something a bit more complicated. And so this table explains how the writers of that paper linked the pooling layer 2 to the convolutional layer 3. So the process explains that yes, they are linking that layer with that layer. So the details are not important, but here it is to explain that you can trick a little bit the network. You can define some specificities in order to extract more and more information and avoid symmetry in the network. Here you can, because you determine which layer is connected to each layer, which feature map to which neuron, you can really increase the complementarity of the information and avoid just to repeat the same information by symmetry. Here I would like to give you a small intuition about what is a kernel. So you have here two kernels for two-dimensional kernels. Let's say one for vertical change and one for horizontal change, called Sobel operator, and it's used for edge detection. And here you can see that if you apply the X matrix just previously shown and the Y matrix, you can end up with that kind of image. And if you apply both, you have that kind of image. So here the operator, or the matrix, or the kernel is already defined. So okay, it's a function well defined. But in the network, we'll train the parameters, so we won't use something already defined. But here, just to give you an intuition that with that network, you can expect understanding. If you are dealing with images, you can try to plot the images after each operation, after each convolutional layer, in order to see what information is extracted with that layer. So it's a tool that you can also use, and you can see that kernels are interpretable for the human brain at the first stage of the network. It can be interpreted. We have three types of layers: convolutional, pooling, as I told you, to reduce the sensitivity to translations, and finally you can finish your network with fully connected layers, as they did in Lelets 5. They applied 2 or 3 fully connected layers. And in that case, you can have different functions like rectified linear units. There is a lot of research about which functions are the best to avoid learning slowdown, etc. So you can find many information about it. Okay, so I won't go here into details. I just wanted to put some slides about backward propagation. So for you, if you forgot about it, you can go back in my slides and remember it. So the basis of backward propagation is that kind of a function is that you will base all your approach on the gradient, and you will apply gradient descent, and you will update the parameters like that. So again, backward propagation. Okay, so why are deep neural networks hard to train? It's the explanation is based on unstable gradient problem. So because you have a lot of layers, a lot of neurons, you have to propagate the gradient. And as you can see here, if we start with a sigmoid function, so the sigma can be a sigmoid function, you have the maximum of the derivative, that is 1 out of 4. That means that if you apply backward propagation and that you end up with that kind of function for a very, very basic network, like composed like that, so it's only 1 neuron for each layer. So it's very basic, but it's just to have the intuition. You can see that you will multiply each time by 1 divided by 4 at maximum, and so you will have a very, very small gradient, and that means that the change in the cost function will be very small. And so that is one of the main problem with deep neural networks when you have many different layers. And you could have also, here it's called the vanishing gradient descent, because the gradient vanish when you when you go back into the layers. But you could have the opposite. You could have exploding gradient descent. So yeah. Now I would like also to give you some intuition about the mathematical approach behind convolutional neural networks. So it's also based here on backward propagation. The basic idea is pretty much the same. Maybe just here you can see that we apply a function sigma to something that is combining the output from the previous layer represented by L minus 1 to have the inputs for the neuron of layer L. And what maybe differ from the basic network is that you don't compute it on all the input layers, the inputs from the previous layer, but here you will restrict yourself to dimension mm. As I said, it's your local receptive fields that has here dimension mm. So it's maybe the only big difference with basic neural networks. So you can see to m minus 1, m minus 1. So here is basic decomposition for the gradient. I won't go into details. You can derive the deltas and you can update the previous layer, but it's really the same as for basic neural networks. The only difference is that here, because you have weight sharing between neurons for the same feature map, you have to add all the deltas for the same feature map, because you have the same weight that is appearing in each of these derivation. So you sum you sum all the weights because you have weight share. It's the same idea as the basic one. Okay, so here the paper I told you a lot about explain two different approaches: batch gradient and stochastic gradient. So batch gradient is, as you might know, maybe it's just applying the gradients on all the training sets, while stochastic gradient is much more online method. So you base your update on one sample or on mini batches. Mini batches are like a compromise between both methods. Stochastic gradient is better if you have some redundancy, because you don't need to go through all the samples in the training set, but you can really limit yourself to some samples and hope that you have some redundancy in your basic training sample. You have some methods for to learn for the learning rates, and one is explained in the paper from LeCun, etc. When should we use that kind of network? A lot of companies like Google, Facebook are using deep architectures and convolutional neural networks. It can be applied to a lot of different fields. It's as I told you, when you have spatial information, you can use it, like voice recognition, sign language, image classification, digit recognition, because you can have temporal. Temporal is spatial. If you have time series, it's like spatial as well. So you can really apply it to a lot of different fields. Another paper that used convolutional neural networks. So here I will give two other papers. I will present you two other papers in order just to give you some intuition on when to use it and what kind of networks, how do that kind of networks look like. So one of those papers is sign language recognition using convolutional neural networks. You can see the plot of the graph of the network here, all the connections. And what was interesting in their paper is that they divided their approach into two parts. The first one is the convolutional neural network that was used for feature extraction, and then they applied a basic artificial neural network for classification. So it's the same approach as previously explained, but it's just that mentally they divided conceptually they divided the network into parts, but it's the same. They just finish with fully connected layers as in the Lenet 5 network. Another paper is ImageNet classification with deep convolutional neural networks. So they also developed and trained a convolutional neural network with 5 convolutional layers plus pooling and 3 fully connected layers at the end of the network. What was interesting here is that they plotted the convolutional kernels. So remember, a kernel is made of weights and a bias, and they plotted that with small pictures. So here it's not really interpretable, but just to give you an idea of the kernels, and that you can try to graphically see the kernels if you determine for each value like a color. So here you can see a plot of the 96 convolutional kernels for the first convolutional layer. So a lot of people working with that kind of network try to visualize what they are doing through images like that. What are the main training issues? You have overfitting, that is partly reduced by the weight sharing because you reduce your parameters, and as well the saturation, learning slowdown. So it's a bit the same as for other big networks. It's that you have some functions that when they are applied, they risk to slow the learning, and so you have to deal with that. But it's a basic, not basic, but it's a problem that is already addressed in the literature. You have some solution paths that could be used here, like dropout methods. You randomly choose which weights, which nodes will be removed from the networks, and you change the random nodes chosen at each step, and so it helps to reduce overfitting and to make it less sensitive to specific training samples. You also have data augmentation. So here you try to increase your training set by applying some translation distortions. It's to create more examples and to make it less sensitive to that kind of distortions. And then you have the choice of hyperparameters like learning rate, mini batch size, weight initialization. You have also a lot of literature talking about weight initialization, regularization rates, etc. So you can really find a lot of literature addressing all those problems. And in fact, it's maybe the most difficult in that kind of model is that you have a lot of hyperparameters, and you have to try to use it and to see what in which situation you should focus on one. And yeah, okay. So just a small introduction to unsupervised neural nets. So you can also use convolutional neural networks for unsupervised problem, like the auto encoder. Here you try to predict your inputs, and why is it interesting is that you can use it to reduce the noise, because you will use like bottlenecks, or you will reduce the dimensions, and then you will go back to predict your inputs. So you will have a concentration of information, and then back trying to predict your starting information inputs. And so you will try to find similarities and to clean the information to go back to what you started with. Another interesting model is generative model. You try to predict the distribution, to analyze the distribution of your inputs. And you have a lot of models like restricted Boltzmann machines, deep belief nets. So you have a lot of research, active research in that topic now. You can find a lot of papers about those methods on the internet. To conclude, convolutional neural networks is an attractive cutting-edge model. It tries to extract spatial information to make your model invariant to spatial translations. You don't need prior feature extraction. You don't need to have specific knowledge in a topic, so you don't need to dig into biological information, etc. And you can use backward propagation, very well-known method, so it's easy to apply. I mean, mathematically it's easy, then in practice it's more complicated, but you have to keep in mind that you have a high number of hyperparameters, as I told you, learning rates, and here you add a lot of other parameters like the shape of your pooling layer, the number of feature maps, etc. And you have more general training issues like overfitting, loading, slowdown, and yeah, it is partly addressed by weight sharing, but you still have to keep that in mind and to avoid that. Okay, so here my presentation resource. If you need more information, you can check it. Thank you. So if you have information, a question, I can try to.
I have a question about the first article you mentioned, the one about Bengio and other people. And it's about the structure of the neural network in the sense that that is a design decision that is made by the authors of the article.
Yeah.
Is there a way to, I mean, that is due to the expertise of the people doing the network. Have you seen some articles in which also the architecture of the network was in some sense generated or optimized, or is in most of the articles you have seen just a matter of they tested and that is the architecture that works better?
Yeah, that's a really good question. I'm not aware of that kind of paper, but it showed that here in that paper they explained that they trained a lot of different architectures and they finally ended with that model. So yeah, it's really up to you to decide the architecture of your network, and it shows that you cannot be sure that it is the best architecture. You just you just train, and maybe you I don't know, I'm not aware of it, but maybe there is some research on how to some principles, some guidelines to determine the architecture of the network. Maybe you can find it. Yeah, but I don't know more about it.
Okay.
But it's really interesting because yeah, it is one of maybe the most difficult problem in that kind of deep architecture. You have a lot of parameters to choose, and yeah.
Okay, thank you.
Can you go back to slide 30?
Okay. This one?
Yeah, this one. I did not understand well what is this representation.
So if you have your first input layers and then you have the convolutional layer, here they have 96 convolutional kernels. That means that they have 96 feature maps because each kernel is associated with one feature map. So if you just, I can here for example, so just to show that you have your input video, that is your inputs for your model, and then you have here 4 feature maps. That means that for each feature map you have one kernel that is made of weights. So you have the same weights for one feature map, and then here you have 4 kernels. Okay, and here what they try to show is that for their first convolutional layer made of 96 feature maps, you can try to plot the kernel, but it doesn't have to my knowledge, I'm not sure, but to my knowledge it does not really have a big information here. It's just to show that if you have like kernels of size 11 times 3, you must have for each point you have one weight, like the weights, you know what I mean. And you can try with the value of the weight, you can try to determine it's a color. It's a color, and so you can plot the kernels. But for me, I'm not an expert in it. So for me, it's maybe I don't see really the point of doing that. But what is interesting is that you have some people that plot after each convolutional layer, they plot the image, and then they apply the function, and they plot again the image, like I showed with the kernel, the Sobel operator. So with that kind of plot, you can see what was the goal of the convolutional layer. So there is a great video you can watch. It's the last one, and they plot the image after each function. So you can see the difference. And because the first layer, for example, it might be for edge detection, as I showed with the Sobel operator. But when you go into the next layers, it might be less intuitive because it's more complex. And so maybe for the first layers you can plot it and you can understand with an image what is the filter doing. But when you go to more further layers, it might be less intuitive, and you won't really understand what is the kernel for.
And what about your experience with that? I mean, you use them for the competition. Can you say something about that? About how you tune the parameters? What do you think?
Okay, so I based my script on someone else's script, and then I try to tune it a little bit. So you have to know that a lot of people you need to develop expertise in it, because it's really hard you have so many parameters that you need to know where to go. So that's the first point. If you want to use that, you must address it over a long period in order to develop expertise. What I did is that I try to tune the shape, the dimensions of the layers. And for me, it was a bit random, because I didn't spend so much time on it, so I couldn't give you guidelines on it. But you have a lot of different packages, like Theono or Café, and one website explains the different packages. But maybe
what did you use as a code? It was a Python code.
Yeah, Python code. Yeah, so I only search for Python packages. So you have already some packages that are developed. You don't need to code everything. So you can.
Fast enough, because I mean, it was not implemented in GPU.
No, it was not in GPU. So you can already do something with. Yeah, it was fast enough. Yeah. It was Kaggle competition. So.
Yeah.
Okay. It was based on biological data, biological electroencephalogram data. So you had, I think, 30 or 36 electrodes that were placed on the brain of the person, and they recorded electrical behavior. And the goal was to predict the movements that the person was doing. So the person was doing always the same kind of movement with her hand, like that. And we had a lot of records of the same movement of the person, and the movement was divided in 6 steps. And we had to say, okay, based on the data, we are in the first step, second step, etc. Here it was more time series. But because you have the brain and the electrodes were placed on the brain, and the brain has spatial information, you had spatial and temporal information, so that kind of network was really great.
Were you making convolution also in time in your?
I think no. In fact, the basic data was like just temporal, but the
spatial.
Yeah, I mean, spatial, for the 36 electrodes, and then temporal. And what he did is that, because I based my script on someone else, he took information, past information, and image sampling. He didn't take all the 20 last points in time, but he made sampling over a period of time, and he decided. So he increased his inputs, and it was like a matrix, but you could see it in a line, just a lot of information. And he considered each point like an input. So he didn't say, okay, I will try convolution over spatial and over temporal. It was combined, in fact.
And then he used the neural network. I mean, this was
Yeah.
to create the features. And then
Yeah, directly, and no previous, because I started with another method, like trying to extract features based on knowledge in biology, and so I base myself on a technique specifically developed for biological data. But afterwards, I saw that that kind of model, and that kind of model didn't need to be really an expert in biological data. It was just you just sampled over 20 points, for example.
Did you try to use these features with another learner, just simply using this input for something else, or?
Yeah, for normal like logistic regression.
So you use that with the logistic regression.
I
you
mean,
didn't use the entire neural network.
No. For final prediction, I used that. It was really really good, like 93% or 90.
Yeah, but why not taking the features generated with that, but with another learner?
I didn't use it. Because it was
possible to extract the features only. And
in fact, you mean features? You mean the input that I gave to that neuron? To that network?
I mean, this is generating features in some sense.
Yeah. I think you could do that. I didn't do that, but you could do that. Yeah.